Hello and welcome to Numeristical. We are continuing our series on Major League Baseball game prediction. We are now in the 15th video of the series. Last video, we looked at the calibration of our individual run scored model. So we had this model where for each team we looked at their hitting statistics, we looked at the opposing team's pitching statistics, created a model to predict the distribution of the runs scored. And we had used that model to come up with the overall prediction on the over-under. And we found some miscalibration in the predictions of that over-under model. That while it was useful for betting, and we could probably make a little bit of money betting on those predictions, um, when the model said it was like 70% likely to be right, it was actually only right about 57% of the time. So we decided to dive in, try to explore that. We looked at the calibration of the individual run scored model and did find some miscalibration. We did find that it was slightly over predicting the probability of low scores and under predicting the probability of high scores. And we concluded that was a contributing factor, but it wasn't really big enough to explain the high degree of miscalibration we're seeing in our predictions. So next we're going to look at this independence assumption. So right now the way we're building our model is we say here's the distribution of runs scored for team A, distribution of runs scored for team B. Let's just multiply those two distributions together, assume that they don't affect one another, and say what's the probability that the total number of runs scored would exceed whatever the line is. In this video, though, we're gonna try to do better than that. And the way we're gonna do better than that is using a technique called nested modeling. So we're actually gonna use those individual runs scored distributions as features in a model and try to use modeling to predict, given these features of team A's run score distribution, given these features of team B's run score distribution, can we predict the total number of scores? And this way, if there actually is some dependence, that should come out in the modeling. And we're hoping that this will improve our overall predictions and hopefully get rid of some of this miscalibration that we saw. So that's where we're headed. Before we head to the notebooks, a couple of announcements. First, as always, if you could like the video and subscribe to the channel, it would really help me out a lot. So thank you very much if you could take a second to do that now. The second announcement is if you'd like to join our Discord channel, I'll put an invite in the description. It'll be good for 7 days. We're getting more traction, more people are joining and discussing stuff related to baseball prediction and machine learning in general. So it's a great place if you're interested in these topics, want to dive a little deeper. It's a great community to be a part of. Third announcement is that I will be in Boston next week speaking at the Open Data Science Conference. So if you happen to be in Boston, happen to be at the conference, please come up, say hi. It'd be nice to meet some viewers in person. And with that, let's move over to the notebook. Okay, so in this notebook, we're going to work on how can we predict the over-under using this nested modeling approach. So to review, we explored the calibration of the individual team run scored models last time. Observed some miscalibration. It was over predicting low runs, under predicting high runs. However, they didn't seem large enough, these discrepancies, to explain the high degree of miscalibration in the overall model, where in this category of predictions where we say we should be right 70+% of the time, we were only right 57% of the time. So we concluded, okay, this must be a problem with the independence assumption then. And so to try to address that, we're going to use this approach called nested modeling to do that. So I've run through some of this notebook already to save us a little bit of time. So what is nested modeling? Nested modeling is this idea, and I don't even know if this is an official term. This is just what I've called it to myself. But the idea is you want to use the outputs of one model as inputs to a second model. So in this case, we're coming up with these predicted distributions of here's the probabilities that team A is going to score 0, 1, 2, 3, 4, and so forth, many runs. We've got the probabilities for the team B, the same thing. Now we want to basically give it, here's the final run total. Can you now predict the distribution of the run total given these features being numbers related to the distributions of the first models? So if we can model this rather than having to use this independence assumption, this will help us. So if the independence assumption is not quite true, it should learn the true relationship or learn some kind of correction based on the data. Now here's the challenge, and here's why you need this nested modeling approach is we took our model before and we built it on the training data, and then we made our predictions. We used the validation to determine early stopping, and then we made the predictions on the test data, and then we multiplied them using the independence assumption on the test data to get our final predictions. Now we want to train on the outputs of the model, but the model was developed on the training data. If we use that model to make predictions on the training data, those predictions are going to look weird because they're basically going to be overconfident and basically look screwy, look different than what we would expect to see kind of in the wild, because the model is going to do much better on predicting the things it's already seen before than it will do on new data. So this creates a problem. We need predictions on our training data, but we need the training data to develop the model. So how do we get around this? Well, what we're going to do is we're going to use cross-validation, and this is an approach probably many of you are familiar with. But the idea is we're going to break up our training data into 5 pieces. We're going to train on 4 of the pieces and make predictions on the 5th piece. And then we're going to train on pieces 1, 2, 3, and 5, make predictions on 4. Train on 1, 2, 4, and 5, make predictions on 3, and so forth. So at the end, we'll get predictions on everything in the training data, and they'll all be from slightly different models. But they'll be pretty similar. And the goal is that since these models will be pretty similar to each other, and also similar to this final model that was trained on the entire training data set, and that we'll use to make predictions on the validation and test data, that they'll be statistically similar enough that if we then build a model on those training predictions, these cross-validated predictions of the training data, we build a model on that to predict the number of runs scored, total number of runs scored, that model will then perform well on the validation and test sets that used the full model. So it's a lot to think through, but this is called cross-validation. It's a very common technique. And that's what we're going to do. I want to see how it works out. So the first thing we need to do is to create folds. So the folds are these slices of data that we're going to do. And it's common, 5-fold is a common number to use, just simple enough to do our cross-validation. So to define these folds, now you could generate folds of your training data in a lot of different ways. You could just randomly divide things into folds. What I'm going to do though is I'm going to break it up by year and have an entire season go into a particular fold. And the reason I'm going to do this is because games nearby, so if 2 teams play each other a few days in a row, they're going to look very similar. Most of those statistics will look very similar. Now granted, the starting pitcher will be different, so that'll change a little bit, and obviously the outcomes could be different. But it makes me a little nervous. There's a little more potential for kind of weird things to happen, for overconfidence in the model, if it has one of those 2 very similar data points, almost identical data points, and one's in a training set and another's in a test set. So we want to avoid that. So what we're going to do is we're going to split up the seasons and break them up into folds, and here's the code I'm using to do that. And if we look at the results, basically what happens is, taking 1980, I'm just throwing that out, right? We just used 1980 to build up a lot of our historical statistics. Then fold 0, so I'm going to number the folds 0 to 4, are going to be the 4 main folds of our training data. Fold 0 is going to have 1981, 1986, 1991, 1996, 2001, 2006, 2011, 2016. And so forth. And fold 1, you can kind of see how they all pattern. We're going to just stagger it down. Some of the folds are bigger than others. It's not too big a deal. But the idea is that I also didn't want any fold to represent a very strong particular era of time. So I didn't want to put like 1981 through 1988 all in one fold and have one fold that was just about the 80s. I kind of wanted to mix them up, but I didn't want them to be so mixed up that you would have very similar games in different data sets. So this is using some principles and some intuition I have about that. You could certainly argue with it, and I'm not 100% convinced that this is the best way to do it, but I think it should be a reasonable way to do it. So we've done that, and then fold 6 Fold 5 is going to be our validation set. Fold 6 is going to be our test set. And another thing to point out now, remember the way we built our runs, this DF runs data set, was we took all the home teams and kind of stacked them on top, and then took all the visiting teams and stacked them on the bottom. So if I look at the shape of the data, and then take half of that, which is this number, and I look at the first 5 games, and then I look at the first 5 games in the second half, you'll see the games line up. And this is just to point out what we're doing with the data wrangling. So this first row of the data set is the game Seattle versus Toronto, and Seattle's the home team. So we have the runs scored by Seattle, and we have all the statistics of the Seattle hitters and the Toronto pitchers. And this row, number 96248, is the same game, but it's the Toronto hitters versus the Seattle pitchers. And if you scroll all the way to the right, you see this home hitting. So this tells us that this is where the home team is hitting in this instance, and this tells us home hitting is going to be 0. That tells us the visiting team is hitting. And this is just for structural reasons, because we're going to have to, after we make these predictions, we're going to have to line those up and say, here's the run score distribution for one team, here's the run score distribution for the other team. Now predict the total number of runs scored. Okay. So the first thing I'm going to do is just break up the training data and test data as always. And I've got this test game where this is the game level data on the test set. And again, this is just illustrating what I illustrated before, that if you look at the training data, it has the same behavior where we can split it in half, and it's equally valid for the validation set and the test set. Here's our feature set, and we're gonna build the same model we built before, but what we're gonna do is we're gonna do a loop, and we're actually gonna train the same parameters, same kind of model, but we're gonna do it 5 times. So here's the loop. We're going to go 5 times. We're going to let the training set be everything except the particular fold number, 0, 1, 2, 3, 4. And the test set is going to be that fold number, 0, 1, 2, 3, 4. And we're going to create a model. We're going to train it using the training set. So everything but one fold. Evaluate it. We're going to kind of cheat a little bit, which is okay. And that we're going to use the evaluation set to be the test set. So we're going to sort of double purpose it. And that's fine, because we're not, that should be a minor discrepancy, and we're not cheating because all of this is part of our training set anyway. So we're still not going to be looking at anything in the test set to develop our model. And then what we're going to do is we're going to create this big run dist train is going to have our whole set of predictions. So we're going to fill this in fold by fold. So after one iteration, we'll fill in some of the rows. After the second iteration, we'll fill in more of the rows. And by the 5th iteration, this thing will be full of the relevant predictions. So we run that. I should say this takes a while because we've got to run it 5 times. So this probably takes about an hour to run. You can see it goes through 5 loops. And then we're also going to train the same model as before on the full training data using the valid set for early stopping, and then making predictions on the valid set and the test set for this model. So let's review what happens at the end of this. At the end of this, I've got run score distributions. So you can think of these as every prediction, remember, is basically 17 numbers that give us the probabilities of 0, 1, 2, 3, 4, up to 16 or more. So I've got these 17 numbers for every team in every game, right? So for a particular game, I'm going to have 2 of these rows. and we're going to know kind of how they're lined up. We have one down here, and then we have one in the same place in the second half. So what do we want to do? We've gotten these sort of cross-validated training predictions. Now we want to kind of take the second half of our data set and kind of move it up and put it alongside of the first half, so that we'll have not a square, but a data frame where we've now got essentially 34 numbers representing the two probability distributions. And we're going to use that as our training data, and then we're going to take the total number of runs scored, we're going to build that up and put that as our Y. And we're going to build a new model that says, hey, if you see these two distributions, what do you think the total score is going to be? And this will allow it to learn how those numbers, how the probability distributions translate into a total, rather than just applying that independence assumption. So this is just to check that, hey, we're still getting a reasonable number for a log loss, that this distribution seems to be, making good predictions. Now, what I'm going to do in these three lines is, so I've got a probability of exactly 0, probability of exactly 1, and probability of exactly 2 for each of the teams in that particular game. But those numbers, I think, will not do as well as features than if we do the cumulative distribution function. So I'm going to say, what's the probability of 0 runs? What's the probability of 1 or 0 runs? What's the probability of 2, 1, or 0 runs? And so forth. So I'm going to use the cumulative density function rather than the probability of just that particular value. And the idea is that these numbers are more comparable. If I say, hey, this team has a bigger chance of scoring less than 3 or less runs than this other team, that means that this team is certainly lower scoring than the other team, roughly speaking. Whereas if I just say, hey, this team is less likely to score 3 than this team, I don't know if that's because this team, they're not likely to score 3, they're likely to score 6, or whether they're unlikely to score 3 because they're very likely to score 0, 1, and 2. So the probabilities of any individual slice are not quite as informative as sort of the cumulative saying, what's the probability you're going to score 3 or less? So I'm going to create these cumulative density functions, and I'm actually going to throw out the last row because the last number is always going to be 1. So we can throw out that last column. So we end up with 16 numbers for each team in each game. And now I do a bunch of wrangling here where I essentially I break it up into train, valid, and test sets. I get for team 1 is the first half, team 2 is the second half, and then I stack these up to make the data be in the shape that we want. So here I create, here's for team 1, here's for team 2, and then I'm going to over here stack them H-stack horizontally. So I'm going to stack these two things horizontally to get a train, valid, and test set of this nested data. So let's just run through that and I can show you a little bit what that looks like. Okay, so here's what this looks like after I do all of that. And this is just a sample of 10 random rows in our training set. But you can see I have the run distribution 0, run distribution 1, run distribution 2. These are just the names that I gave. This is for the home team. So what this is saying is that in this particular game, the home team was 6% likely to get exactly 0 runs, 17% probability of getting 0 or 1 run, 31% of getting 0, 1, or 2 runs, and so forth. So basically, the bigger these numbers are on the left, essentially means they're a lower scoring team, because it means they're more likely to have a lower score. So this was probably a higher scoring team because they're only 2.7% chance to get a shutout, to be shut out. So we get this for the home team, we get 16 numbers. You can see by the end, we're very, very likely to be 1. So 1 minus this number is the probability that you're 16 or more runs. And then we got the same thing for the second team. So this is our training data. We're going to say, hey, here's 32 numbers that tell you about the distribution, what we predict for the runs scored for each team. And then we're going to tell you what the total number of runs actually was. And we're going to say, hey, machine learning boosting model, can you make a nice prediction? And so now that we're going to do that, we're going to use the same probabilistic regression technique, this corsage algorithm. And we're going to train it and say, given this set of 32 numbers, can you predict the distribution on the total number of runs scored? So that's going to run now. So we got to wait a sec for that to finish. Okay, so that finished training. And now we can make our distributions on the test set. So we see this is the log loss that we get. Again, hard to really know what that means. What we can do is say, compare the log loss that we had if we just used one tree versus the log loss we got at the end. You can see that the training did improve our performance. Not by a ton, but by some. But now let's look at some of these predicted distributions. So here's what our model is predicting for the first 9 games in terms of the run score distribution. Now you'll see this is pretty interesting. And one thing you'll see is this: you've got this kind of up and down pattern. And you might say, what's going on here? Why is it predicting this? And there's actually a very simple explanation for that, which is that even numbers of runs scored, you could see that 4 and 6 and 8 end up being less likely than the odd numbers like 5, 7, and 9. And the reason for this is that you can't have a 3-3 game that has 6 total runs, right? It'll go into extra innings. And so this creates a bias in favor of an odd number of runs. And it's cool that the model, learned this, and that the predicted distributions that we get actually reflect this effect. Now, when we did the independence assumption, I actually put in a little bit of a correction to say if the game is exactly, if we're predicting a tie score, and that is exactly the line. So, for example, if the line was 8, and the model predicted 4 runs for this team, 4 runs for that team, I had to count that as going over rather than a push. This little adjustment I made to the model. It was an option in that function. So the independence assumption, the way I applied it, should kind of reflect this. But you can imagine if I just put a pure independence assumption, you probably would not see this effect. So this is an example of how the nested modeling can learn something that, for example, a calculated model would not be able to learn. So this is a generally good sign. It makes me have some confidence that our predicted distributions have this staircase pattern. And to show that this is actually true in the data, we can look at this is just the histogram for the number of runs scored. And you can see this staircase pattern does happen in the actual data. Overall, you get more games with odd numbers of runs scored than with even numbers of runs scored. So now let's again do some wrangling to get our probabilities of under, over, and a push in our test set. So, and these are the histograms. So here's the probability. The under probabilities I predict, so you see it still goes up pretty high. And over probability is not quite as high. So we still see this bias where it likes the under a little more than the over. But now let's get to what we're hoping, what we're hoping to solve, which is this calibration. So what I'm hoping now is when this model says, hey, I'm 70% or more likely to go under, I'd like to see that this happens actually 70% of the time. So let's see if that plays out. And actually we see again that it doesn't, that this is poorly calibrated, right? When our model is saying that the probability, over here, this is where we're seeing 0.7 or higher. And if you zoom in, you'll see we're getting more than 50%, but we're not getting 70%. So we're still running into the same problem. So this suggests that the independence assumption was probably not the culprit either. So I thought when I started out doing this, I expected this to do a lot better. I expected this to sort of correct some things in the independence assumption. But I'll get to why in a few minutes. I'll get to why I think this is happening. And if we look at the over, it's kind of the same issue going on. Now if we look at push, we'll see the probabilities of pushes are pretty well calibrated. Now it looks like I'm consistently under-predicting a little bit, so I might be under-predicting the probability of the push, but at least everything's kind of within the error bars. We don't see anything sort of systematically off the way we do on this one. And now if we do the same kind of betting analysis that we did with the other model, where we say, okay, like let's look at how, if we were to bet on this, we see we're getting very similar to what we had before. So you see, for example, this 0.2 threshold, we would have gotten 197 correct and 151 incorrect. And if you remember last time, it was 197 and 147. So this seems to be making pretty close to the same predictions as the other model. It just leads me to believe that this is not changing the model too much fundamentally. So we're still making money on it. It's a tiny bit worse, but not significantly enough that I think it's any sort of major difference between the two. It just seems like it just didn't really help. Didn't make things worse, but didn't help much, if at all. So why is that? So to get into this calibration thing a little deeper, I decided to test a couple things. And one is saying, let's see if rather than betting the Vegas line and looking at those probabilities, what if I just picked one line? I just said, for every game, I'm just going to see, is it 9 or higher or 8 or lower? And I got that by just saying the typical over-under line is around 8.5. So let's just suppose that the line was 8.5 for every game. Now my model would give a probability for any game that it thinks it's over 8.5 versus under 8.5. So I could calculate those. So let me do that. And let me see how the reliability diagram would look for that. And you see it looks a little better. At least it's very consistent, right? Now what it shows is I'm under predicting a little bit for the high values, but still kind of within the margin of error. But at the lower values, when I say the under is less than 50%, it actually ends up being considerably more than 50%, considerably less than 50%. And similarly, when I look at the overs are coming in kind of more likely, especially for these 3 bars, which is even when I don't think even when I think the over is less than 50%, it's coming in at 50%. And for these 2 bars where it's more than 50%, it's coming in at well more than what I predicted. So that's interesting. And this goes along with this bias we saw in the run scored model, where we said we're under predicting the high run scored, over predicting the low run scored. So that would mean that the over is kind of going to happen more often than we think, and the under is going to come in less often than what we think. And these two plots reflect that, but reflect it to sort of a reasonable degree. This is sort of what we would expect given that the miscalibration that we know about in our individual models. The other thing I wanted to do is now say, let's suppose I just choose a line randomly. So I picked a line to be anywhere from 5 to 15. And I allowed halves. So 5, 5.5, 6, 6.5. I just said randomly give me one of those numbers and have that be a line for a game. So I'm going to pretend Vegas is setting the line randomly, and I'm going to look at my probabilities. So my probabilities might be more extreme now. If Vegas happened to pick a very low line, actually it's going to be a high-scoring game. I might have a very high probability. But I want to see if my probabilities are well calibrated in this regime, where the line is just a random number rather than a line set by the Vegas market. So let's see how we do there. And this is for the under probabilities. And you see we're pretty well calibrated. Everything's kind of within the error bars. Now I will say we're consistently under the line and almost never over it. So again, it seems like we're over predicting the runs by a little bit. So we're over predicting the probability of a low score, the probability of the under. So again, this corresponds to we know that our model, these individual run scored models on the test set, were kind of a little bit too low scoring. And so this jives with that. But again, this is reasonably well calibrated. This is kind of what we expect. So what's going on? And now if we look at the over, we see the same thing. Again, pretty well calibrated, but a little bit systematically under predicting the over. And you got a couple that are a little bit outside the bars. But this says that, so what's going on? So this says, in general, when I take my run scored model and I do this nested model, and you just randomly pick a number of run score to go over or under, and I set my model's probability, it's pretty good. It's pretty well calibrated. It's off by a little bit. We tend to underestimate a little bit in this test set area, and that could be distribution drift, model drift, something like that. But it's generally doing pretty good. But then somehow, when we look at these extreme games, so let's go back up to our first one. When we look over here, we're kind of okay here, but like once we start getting into regimes where we're saying, hey, the under is more likely, we're kind of overdoing it. So what this suggests to me, and this took a while of thinking and pondering to try to come up with this hypothesis, is that what's happening in these games, especially let's focus on these games where we have a high probability, where we're saying that the under is very likely. What has to happen for us to say that the under is very likely? Well, it means two things. It means that sort of our assessment of the game is on the low side compared to what Vegas has said. But you have to remember the Vegas model also is going to have some information we don't have, right? They might know whether the pitcher's arm is hurt a little bit, whether the bullpen's tired or not. You know, might reflect things like which pitchers are going to be available from the bullpen. So the key to understanding this, I think, is that the line, the Vegas line, reflects some information that's not in the model. And so therefore, when we get these more extreme results are happening when sort of, you can think of it as two pieces. There's one piece where it's like our sort of mathematical evaluation differs from the Vegas sort of mathematical evaluation of it. So we've got to have some discrepancy there. But then we also might have an additional discrepancy where Vegas has some other information that's outside our model that's causing it to move the line even further away. So the idea is when we're far from 50%, it's probably because both of these things are happening. Our mathematical assessment is different than their sort of mathematical assessment. And also there's maybe some extra non-mathematical information or other stuff that's not in our model that has caused Vegas to move the line further away. And so these extreme results, when we have a high probability over here, this is happening because these are also the games where Vegas has some information that's not in our model that's causing the probability to go the other way. And we're kind of selecting out those numbers. So that's what I think is happening here. And this is something that if you start working through your head, it makes sense. It's like, okay, when I have an extreme prediction, there's probably something I don't know that's factored in the Vegas line. Otherwise, why would I be so far away? And so when I have this big prediction, probably it might be better than 50%, but it's probably not as extreme as I think it is because there's probably some mitigating factors that aren't in my model that are showing up. And this shows up when we're looking at the Vegas lines and how they set them. But when they randomly, if you just randomly choose a number to bet over and under, then that's going to be less of an effect. So that's what we're seeing here. And that's what we're seeing here when I just sort of randomly pick the line. I'm generally doing pretty well, except for like maybe a little bit of this scoring bias that we discussed. So that's what I've come out of this with. So my conclusions are that the information inherent in the Vegas line, this is probably why we're miscalibrating. Because when we've got a high score, it means that there's something we don't know that's not in our model. And that should probably means that we're going to systematically overpredict that probability. Now we know our model tends to overpredict low scores and underpredict high scores, so now we're seeing a lot of that evidence. And again, that might be just what it learned in a discrepancy between how things behaved in the training set and training data and how things behaved in the test set, because we know there's drift over time. Another conclusion, that this independence assumption does not seem that bad. I had before I thought about this deeply enough to sort of realize that we're getting this bias from stuff extraneous to the model. I thought the independence assumption must be the culprit, but now I don't really think it's true. And if one thing I'd like to do on my own is just go back and compare these models, compare the previous model to this model, and see kind of how different they are, and do a direct comparison. So that's where I'm going to leave this video. So in terms of next steps, what can we do next with this? Well, we could try to dive deeper into the causes and solutions for this miscalibration that we know about. And again, I think it's likely just sort of distribution drift, model drift, where basically like life is different in the test set than in the training set. So even if we do a really good job learning from the training set, we're going to have a different world in the test set. And we could try doing some calibration, or what's called conformal prediction techniques. That helps though if you know what you're trying to calibrate to. And it's not totally clear what we should calibrate to. I could try calibrating to like the validation set year or something like that, but we don't know whether that year is going to be representative of the test set either. So that's sort of a very subtle thing as to what's the right thing to do there. Another thing we could do is to switch gears a little bit and say, well, we use this nested modeling technique to predict the total number of runs scored. We could very easily use it to predict the run differential, right? And rather than saying runs home plus runs for the visiting team, do runs home minus runs for the visiting team. And see how well we're able to do that, and see whether we can do point spread bets and if there's anything to be had there. And similarly, we could use all of that, all of these techniques and ideas, including with the run differential, use all of that to better predict the money line. So I think the latter two are probably where I'm going to go with this next. And so I hope you'll join me further as I work on that. So thanks again for joining me today. Again, if you could take the time to like this video and subscribe to the channel, it would really help me out a lot. Join the Discord channel if you feel so inclined. I'll put an invite in the description. And if you happen to be in Boston at the ODSE conference, please come find me and say hello. And other than that, in the next video, we're going to, again, advance some of these techniques, probably start looking at the run differential and trying to see if we can better predict point spread betting and money line betting by bringing some of these ideas around the run score back into that prediction mechanism. So I hope you join me for that, and have a great day.